Hello and welcome. I received a question about part 4, video part 4 of the transient solution of the mixing problem. So I'm just gonna go through it a bit before I talk about the question. So you remember that we wanted to solve the transient condition of the mixing problem, where we said we didn't assume that there is a steady state in part B of it. So we wanted to know when to reach the steady state, and we said that would take basically infinity of time, and in engineering problem, infinity of time is not a problem with us. We're not intimidated by the concept of infinity. Actually, we approximate infinity to a definite and finite number. So what we did here basically is we applied it on the system level. We applied the mass balance on the system level, and we calculated it. We ended up with this differential equation based on the mass balance. So I got two inputs here and here, which is 2 cubic meter per second concentration of 50 milligram per cubic meter, and 1 meter cube per second, the same concentration. And I have 3, so those are my inputs, and I have one output, which is 3 of the concentration of C2 multiplied by the concentration 3 meter cubes per second multiplied by the concentration of the C2 tank. And we just assume, so this is V, which is the whole volume of the system, which is 4, because we have 4 tanks, each one of them is 5 cubic meter. That was given to you from the question. So again, we said this is not a valid solution, this is only an approximation. So this is an approximation, and we said this is okay to do this approximation because this is like directly mixed. And we, again, for the scope of this question, they didn't ask us about the exact concentration of, for example, C2 or each one of the tanks along the time. It just want to know when it's gonna be again steady state, when it's gonna go to steady state again. And as we said, as it is, like we said, infinity, we said that we're gonna use the tau, or the time constant, to actually approximate or to give finite concept of infinity. So again, the volume is the volume of the 4 tanks here in this differential equation. And I already assumed that, you know, the 4 concentration are equal. Again, this is not a valid assumption. This is only approximation. We said all of them equals C2. So again, this is only an approximation based on a mix directly. So its approximation is not a valid assumption, but it's like partially valid. I don't want to say partially valid. It's not really that far of assumption, but anyway, what we need to know, what we need to do is we need to calculate the tau or the time constant. This approximation won't change the time constant. It will give us the exact time constant that we need. So I got this differential equation. I want to approximate it to 4V. So this is so I see where's the confusion coming from. So this V now is 4V. So this V is the capital V, which is the volume of the whole system, which is 4 by small v. Doesn't look like small v, so I'm sorry for that. Maybe that's where the confusion came from. So this V is the volume of each one of those tanks. So this should be small v here. So I will just, you know, strike through it just to let you know. So this is small v. So 4 tanks by small v to get the capital V. So 4, which is 4 tanks, multiplied by 5. I want it to look like this. I want the form to look like this. So I tweaked it to get it into this form. So that's why I I could have, divided here by 3, for example, but I want to show you this form, which is the form that we used in the steady state problem to solve it in the steady state. But here, because I want tau, I needed it in this form, which is this form, which is tau multiplied by c naught plus c equals a function. So our function here is like, it's 50. It's a constant, but still a function. So the other question is, what is the g? So our function here is c. I just wanted to tell you that for any function that has this form, this is gonna be true. You don't need to work it out. This is going to be true for any function of that form. You could look at it later, and so this is g5 compared to g infinity. G infinity is when it's gonna go again to a steady state, so after a really long period of time. So this is compared to at 40 compared at g infinity, and this is the same thing, like at 1 tau, and this is actually this would be always right, approximately right, if you got this form, which is a constant multiplied by the derivative of the function plus the functions equal another function. So that's why I change it. I actually want it to be in this format, so that's why I divided here by 20, then I multiplied everything by 20 divided by 30 to get it into this format. So again, we used Laplace transformation to solve it. You didn't need to solve it. So again, after this point, this is beyond the scope of the question. I think it's important for you to know, but also it's important to know that this is beyond the scope of the question. So I just solve it using Laplace transformation. You could go back again to it, but I'm gonna go back a little bit on talking about the time constant. So again, this is gonna be right for any differential equation that have this format. See the format here. And this is compared to, okay? So I compare f at n multiplied by tau to f at the infinity. I want to show you how we work it out here in this format. So again, this is the change rate from t1 to t2. So if I have this function which is start from 0 or start from wherever it is, so if I took the function at t1 minus the function at t0, the rate of change is going to be, for the first tau, is 63%. After 2 tau, gonna be 86.5% at 2 tau. At 3 tau, it's gonna be 95. 4 tau, gonna be 98. Again, this is true for every differential equation that has this form. Not only for this, but anyway, if you want to make sure of this particular problem, this is the function of concentration, the approximated function of concentration that we solve or we obtained using Laplace transformation. So if you want to calculate the change rate, it's C2 at whatever tau you want, so 1 tau, 2 tau, 3 tau, minus C2 at 0, which is the initial concentration, divided by C2 at infinity. So C2 at infinity, it would be 50, right? You could do it by, substitute infinity here. If you substitute infinity here, that means this term will be turned into 0. So e to the minus infinity would equal 0, right? We already worked that before in one of our tutorials. So 50 would be, so C infinity would be 50. And again, this is the whole assumption of how we started it. So you could say that C5 multiplied by C5 multiplied by tau minus C0 divided by 50 minus, which is C infinity divided, not minus P50, it will give you the change rate at 5 tau, which should be approximated to 99%. I hope that answered your question, and if you have any question, just email me this night. I'll try to answer everything if I can before your exam tomorrow. Thank you very much.